This video is a review of simple harmonic motion, mechanical waves, and sound for AP Physics 1. And I'd like to start to talk about simple harmonic motion first. Simple harmonic motion occurs when an object is oscillating back and forth about an equilibrium position due to some restoring force. And that restoring force needs to be proportional to the object's displacement from equilibrium in order for it to be simple harmonic motion. And so there are a few things there that I want to point out. First, the object is oscillating, so it's going back and forth. There's a well-defined equilibrium position. So for example, there's a little mass spring system that I've drawn below. The equilibrium position is this middle position which I've labeled 0. And in order to cause the object to oscillate back and forth, there needs to be a restoring force. And the reason why we call this force a restoring force is because it always points toward the equilibrium position. So for example, in my mass spring system, when the mass is at the positive amplitude plus A, the spring is stretched, and therefore the spring force pulls on the mass back toward the equilibrium position to the left. And when the mass is on the left-hand side, at the negative amplitude, the spring is compressed, which would be pushing on the mass to the right. And because we know that springs, or at least most of the springs that we study, obey Hooke's law, which is F equals kx, that is, the spring force is proportional to the displacement from equilibrium, with a proportionality constant there, k, which is equal to the spring constant, then we know that the more the more that the spring is stretched or compressed, the bigger that force is going to be. And what eventually happens is you pull this object and it's oscillating back and forth, and it oscillates with a regular period. And we know that the period of that mass spring system, which I'm writing here as Ts, is equal to 2 pi times the square root of m over k. So if I change the mass, then the period will change. And if I change the spring constant, the period will change. But the period doesn't depend on things like the amplitude, for example. The same thing is true of a vertical mass spring system, a mass spring system that's hanging and bobbing up and down. There is an additional force exerted on that mass spring system, but the same period equation applies and the same physics is happening. So we just talked a little bit about a mass spring system. It has a well-defined period that depends on the mass that's attached to the spring and the spring constant. Another system that we talked about when we studied simple harmonic motion was the simple pendulum. So if I displace a pendulum from its equilibrium position, and the equilibrium position of a pendulum would always be this vertical position here. And so if I'm displacing a pendulum, it's better to talk about the angle that it's displaced from equilibrium instead of a physical, like horizontal distance, like for the mass spring system. And the period of a simple pendulum depends on the length of the string and the acceleration due to gravity near the pendulum. Similar to the way that the mass spring system has two variables that affect it, the same thing is true of the pendulum, but it's different variables. So for example, one of the important things that comes out of this is that if I change the mass of the bob attached to the string, or the mass of the pendulum, then that should not affect the period of the pendulum. And to point out, the restoring force for the mass spring system is still that spring force. If I stretch the spring force pulls it back toward equilibrium. And for the pendulum system, it's the net force due to the combined tension and gravitational force that always points toward the center. And a couple of things that I want to point out before we start to fill in this table. I'm going to start asking questions about the position, velocity, and acceleration at different points for each of these systems. Before I do that, I'd like to talk about a couple other things. So let's start on the left hand. So actually I'm going to start on the right hand side and talk a little bit about the work done by different forces exerted on the pendulum. So first, we know that work is equal to FD cosine theta. And here, in the picture that I've drawn, the direction that this pendulum would be moving is in the direction of that green arrow. And what I want you to notice is that the tension vector is perpendicular to that vector that I've drawn. And in fact, at all moments in time, the tension force vector is always perpendicular to the direction that the pendulum is moving. For that reason, F and D are 90 degrees apart, and the cosine of 90 is 0. So for that reason, the work done by the tension force is always 0. And if the work done by the tension force is 0, that means the tension cannot change the energy of the object. Next, I want to talk about the gravitational force exerted on that pendulum. We know that the force of gravity is a conservative force. And if it's a conservative force, that means if I move from point A to point B back to point A, then the amount of work done by that conservative force should be equal to 0. A simpler, less technical way of understanding that is on the way down toward equilibrium, the gravitational force speeds up the mass. And as it goes away from equilibrium, as it's rising up, the gravitational force opposes the direction of the object's motion and therefore slows it down. So it speeds it up on the way down, slows it down on the way up. And so in going from point A to point B back to point A, the amount of work done, the net amount of work done by the gravitational force will be equal to 0 because it does positive work on the way down and negative work on the way up, and those will add up to 0. And so for a pendulum, the forces that are exerted on the bob of the pendulum cannot do work on the bob, or at least if they do work, it adds up to 0. And if no work is being done on the pendulum, then that means its energy can't change. And so we should expect that the pendulum bobs back and forth forever because none of the forces acting on it can change the amount of energy that it has. However, we know that for practical purposes, the amount of energy that the pendulum has does go down due to resistive forces. Right, so maybe there's some friction between where the knot of the pendulum is at the top and whatever it's anchored down to, and maybe there's some air resistance between the bob of the pendulum as it moves back and forth. So slowly we could observe some dampening of the oscillations, where if we graphed the amplitude of the wave as a function of time, we would see it would have large amplitudes, but then maybe after several oscillations it would start to die down and eventually come to rest. And we call that damping. The amplitudes are getting less and less. And now quickly let's look over at the mass spring system. Similarly, I know that the spring force is conservative because when the mass is on the right hand side, the spring force pulls to the left, and when the mass is on the left hand side, it points to the right, which means that as the spring gets stretched or compressed, the spring force always points towards the equilibrium. And so in some cases, the spring force is pulling on the mass to speed it up to get it back toward equilibrium, and in some cases, the spring force is pulling on the mass to slow it down to stop it so that way it can come back toward equilibrium. And so in that case, in some instances, it's speeding it up, and other instances, it's slowing it down. And so the net amount of work done by the spring force will be 0, and it's a conservative force. I also know that the other forces exerted on this mass spring system, like the normal force and the gravitational force, are perpendicular to the direction of motion of the object, and for that reason, they will also do no work on the system. And so for that reason, none of the forces acting on the object are doing work on the box, and therefore we should expect the amount of energy to be constant. It should oscillate back and forth forever. However, we do know, just like for the pendulum system, that the amount of energy goes down, and this is because of resistive forces, right? Maybe there's some friction between the coils of the spring as it stretches and compresses, or maybe due to the rapid motion of it going back and forth, there's some energy losses there, or maybe due to the air resistance of the box. Anyway, we should observe some damping just like we observe for the pendulum. Now let's take a look at this table. So the position at equilibrium, we're going to call that 0. And then we're going to call the position at either one of the amplitudes a maximum position. Okay, so what I'm going to do to fill in this table is I'm going to use words like minimum, or actually I'll just stick to 0 or a maximum, meaning that at each one of these three positions, the position, velocity, and acceleration is either going to be 0 or it's going to be a maximum. One thing I know about the velocity of the mass spring system or the pendulum is that when it's at its equilibrium position, it's going to be moving its fastest. And the reason why I know that is, let's think about for the pendulum, right? When I raise it up and it's on the left-hand side or the right-hand side at its maximum displacement from equilibrium, then I know that it's been raised up the furthest amount, so it has the most potential energy. And as it swings down through the equilibrium position, it's the lowest position that it will ever be, and for that reason, it's going to have the most amount of kinetic energy. And if that is where it has its most kinetic energy, that will be where it has its greatest speed. I also know that at either amplitude, that the pendulum has to stop because it's moving to the right, let's say, it stops before moving back to the left toward equilibrium. And so at either amplitude, the bob momentarily stops. And the mass spring system does the same thing, right? It moves through equilibrium, going as fast as it can go, and then it slows down as it approaches the amplitude. It stops and then turns around. So at the amplitudes, they stop, so the velocity is 0. As the object moves through the equilibrium position, so let's take a look at the mass spring system. As it gets right here, and it's at its equilibrium position, the object momentarily has a net force of 0 on it. And this is true because I want you to appreciate that if the spring was never stretched or compressed, that box would be sitting at the equilibrium position, and the spring would not be exerting a force on that box. And so at the equilibrium position, the acceleration should be equal to 0, because the net force on the object at the equilibrium position is 0. That's why we call it the equilibrium position. But as it gets stretched or compressed, that spring gets stretched or compressed, let's say I move over to the maximum amplitude on the left, the negative amplitude. The object is going to momentarily stop, and the spring is compressed the maximum amount, which means we're going to get the maximum amount of spring force by Hooke's law. And so if we have the biggest force being exerted on the object at that negative amplitude, then that means we're going to get the biggest acceleration. It's the maximum acceleration. And this is also true of the positive amplitude. If I stretch the spring the maximum amount it's at its positive amplitude, then the largest pull from the spring will be exerted on that object. And so hopefully, after filling out this table, you can imagine what the table would look like if I wanted to instead write in the three values for things like the net force or the kinetic energy of one of these systems. Now I would like to take a look at three different graphs which hopefully will help us solidify our understanding of that table that we just drew. I have an object here which apparently has a velocity versus time graph that looks like the one below. And what I see is that at the initial point, at t equals 0, the velocity is positive, and it's at its maximum value. If it's at its maximum value, then I know it must be at its equilibrium position because the maximum velocity occurs at equilibrium. And for that reason, I should be starting my position versus time graph at equilibrium. I also know that at equilibrium, where the position is 0 and the velocity is a maximum value, the acceleration will be 0. So I'll start off my acceleration graph at 0. By the time the point reaches this next red point, the object now has 0 velocity, right? This point is on the velocity versus time graph on the time axis, which corresponds to 0 velocity. So now I know that the velocity is 0, and that occurs at the positive amplitude and the negative amplitude. So I don't know yet which way to take my position versus time graph. But if I look at this graph, if I look carefully, the slope of the line right here that goes through that green point is very much negative. And if the slope of the graph is negative, then that means the acceleration is negative. And so in the subsequent motion of the object, the acceleration needs to become negative. And I know that when the velocity is 0, that's at the maximum amplitude, and at the maximum amplitude, the acceleration is the largest value. And so the acceleration needs to become its maximum negative value, which I'll call minus a. And if the object is experiencing a negative acceleration, that means the net force is pointing in the negative direction. And so let's sketch out a mass spring system really quick and imagine what that looks like, right? If here's where x equals 0, the only way that I can produce a negative acceleration is if the object is beyond to the right of that, because that would mean that the spring force is pulling it to the left in the negative direction. And so once again, I know that for the second dot that I've drawn, that the velocity is 0. If the velocity is 0, the acceleration must have a maximum value. But because the slope of that line was negative, I know the acceleration is negative. And in the picture that I've drawn, a negative acceleration means that the acceleration points to the left, which points in the direction of the net force. The only way I can accomplish that is by being at the positive amplitude, plus a. So for that reason, I should have a 0 velocity, a negative acceleration, and a positive position. So at that point, I would be at plus a, where capital letter A represents the amplitude. The subsequent motion of the object is going to be fairly repetitive, right? That's the whole idea. And so as the object starts to have a negative velocity and is a maximum value, I know that the object needs to return back to equilibrium because that's where it has its maximum velocity. But now this time, as we go through the equilibrium position, the acceleration will first become 0, but then the object will start to experience a positive acceleration. As the object moves through the equilibrium position and moves into the negative positions, the spring will start to push on it to the right-hand side, which we're going to call positive. So if you hadn't caught on to that, the positive direction is to the right. And as we start to experience that positive acceleration, the object will slow down, but it very much now is in the negative region of the position versus time graph. The object will once again stop, as I've noted here, at the negative amplitude. And after it stops, it's going to start to move back toward equilibrium again. When it arrives at equilibrium, it will once again have a maximum positive speed. After it has reached that negative amplitude and moving back toward that equilibrium position that I'm talking about, the acceleration will once again become 0, before becoming negative again due to the fact that the spring or the mass will be heading towards the positive amplitude again. Therefore, my position versus time graph needs to also head back towards that positive amplitude. I would strongly encourage you to go ahead and try to sketch out these graphs for different scenarios where maybe the object starts off at equilibrium, maybe the object starts off at the maximum amplitude or the other maximum amplitude, depending on how you're thinking of it. And also you might need to be able to start with an acceleration versus time graph instead of a velocity versus time graph, or maybe a position versus time graph instead of a velocity versus time graph. Now I'd like to talk a little bit about waves in general. Waves are a disturbance that carries energy from one place to another. And so we talked about two different types of waves in general: longitudinal waves and transverse waves. These are both different types of mechanical waves that carry energy from one place to another. A longitudinal wave is something like a sound wave or like the waves in a slinky, where the particles oscillate parallel to the direction of wave travel. And the mnemonic that I use for this is, since the particles are oscillating parallel to the direction of wave travel, they oscillate along the direction of wave travel. And since it's a longitudinal wave, maybe the fact that they oscillate along the direction of wave travel will help you remember that. I can model a longitudinal wave by using compressions and expansions, or compressions and rarefactions, where the compressions are places where the coils of the slinky are closer together, and the expansions, or the rarefactions, are places where the coils of the slinky are more spread out. A transverse wave, on the other hand, is like a wave that we typically think of like on a string. And the difference here is that the particles oscillate perpendicularly to the direction of the wave travel. And the mnemonic that I use to remember this is that the letter T upside down looks like a perpendicular symbol. And so we remember that the particles of a transverse wave oscillate perpendicularly to the direction of wave travel. And what that means is, of course, that the wave here is traveling, let's say, to the right, and all of the particles are oscillating up and down. Whereas for the longitudinal wave, the wave was traveling to the right, and the particles, each coil of the slinky, are oscillating back and forth to the left. So for the longitudinal wave, they oscillate along the direction of the wave, and for the transverse wave, it's perpendicular. And we know that for a transverse wave, the top points are called a peak or a crest, and the bottom parts are called troughs. And the distance from the equilibrium line up to the peak or down to the trough, but not both, is called the amplitude. The distance between two peaks or between two troughs could be measured in length to be the wavelength, or if we're measuring where we have a graph where it's versus time, the horizontal axis is time, then the distance between those 2 points could represent the period of the wave. Two equations that we need to know for waves in general is, first, on the right-hand side, the wave equation, which relates the wavelength, the velocity, and the frequency. In the top of the equation, we have the velocity, which is measured in meters per second. And maybe you remember that the velocity is determined by the properties of the medium, right? So all waves, all mechanical waves, oscillate in a medium. And for example, if I have a wave on a string, then that string has a certain tension and a certain mass per unit length. And the tension and the mass per unit length are physical properties of the string, and it's those properties that determine how fast the wave travels along it. How quickly I shake my hand back and forth does not affect how quickly those waves travel along the string. The frequency, however, of the oscillator, the frequency of the wave is determined by the oscillator. So if I'm the one generating the waves, the faster I move my hand back and forth, the more waves I'm generating per second, the more numbers of cycles of waves that are passing a point per second. And we measure frequency as cycles per second, which we represent as hertz. And lastly, the wavelength, right? If the speed is determined by the physical properties of the medium and the frequency is determined by the oscillator, which is either the person doing it or the machine doing it, then the wavelength really is just determined by the ratio of those two things. Okay, there's not some third independent thing that determines the wavelength. It's just for a given medium we know the speed, and for a given oscillator then we know the frequency. And those two things can allow us to calculate the wavelength. Now I'm at the bottom of the screen, and I want you to realize that because for a given medium the speed is going to be constant, if the frequency goes up, the wavelength has to go down. If you look at the equation, you could see that wave equation written as v equals f lambda. And if v is constant, so I'm using the same rope, then the tension's not changing, the mass per unit length is not changing, and therefore if the frequency goes up, the wavelength has to go down, and vice versa. right? So at the bottom I have a wave with a high frequency and a low wavelength, a short wavelength. And on the right I have a wave that has a long wavelength but a low frequency. And therefore we are to conclude that the period and the frequency are inversely related. Because if the frequency goes up, like on the left-hand side, then the amount of time per cycle of the wave is going down. Right? Because if I was at a particular point right here, the number of cycles, if I had a little, a wave detector here, the number of cycles of the wave that are reaching my wave detector in a certain amount of time is going up. There's many cycles of the wave coming up, and so the amount of time it takes for one cycle, the period, is going to go down. There's an inverse relationship between those two variables. Frequency is measured in hertz, cycles per second. Period is measured in seconds, the number of seconds per cycle. Another important topic of study with waves was superposition and wave interference. We learned that when two waves meet up, they overlap. That's the first thing they do. And then they create a resultant wave that is due to the superposition of those two waves. So when they overlap, you take one wave and superimpose it on the other, and it's the superposition of those two waves that forms the resultant wave. And after they overlapped, after they're superimposed, the waves continue to move in their original direction. They do not reflect off of one another. And so let's look at a couple of examples. Down on the left, I have these two square wave pulses that when they move toward one another, they combine and form a wave pulse that has a bigger amplitude. And the reason why they form a wave pulse with a bigger amplitude is because initially both of their amplitudes were in the positive or upwards direction. After they overlap and produce that larger amplitude, the wave pulses continue moving in the same direction that they were traveling in. They don't reflect off of one another. Originally, B was on the right-hand side, now it's on the left-hand side, and it's still moving in the same direction. That's kind of like a statement of the conservation of momentum or energy, if you want to try and think about it that way. But in general, you can just remember that waves work in this manner. Now, in general, what I have drawn on the left is something that's referred to, importantly, as constructive interference. Here, the amplitudes pointed in the same direction, so when the waves combined, they produced a larger amplitude. They constructed a larger amplitude. They interfered constructively. And on the right-hand side, we have the same thing happening, but when they meet, the wave pulses were above and below the equilibrium line. And when they meet, those waves are actually right here. You just can't see them because momentarily the positive and negative amplitudes of those wave pulses canceled out and we saw nothing. But that didn't mean that the waves went away. After they overlap, they continue moving on in the same direction that they were traveling. And so they didn't go away, they just momentarily overlapped, and the superposition of those two wave pulses, the resultant wave, was that they canceled. But after they continue moving past one another, B is still on the bottom, A is still on the top. We call this, equally importantly, destructive interference. The two wave pulses, due to the nature of their orientation, they were pointed in opposite directions. They destroyed one another. They interfered destructively. One great addition to the idea of talking about constructive and destructive interference is the idea of beat frequencies. A lot of times when we're tuning an instrument, we might be using a tone generator to try and help us tune the string of an instrument, for example. Maybe we play the tone and we hear and we pluck the string, for example, and we're hearing loud and soft sounds. What's happening is those frequencies are close to one another, but they're not equal, and so the difference between those two frequencies is generating a beat frequency, which produces loud and soft sounds. And those loud and soft sounds are generated due to two frequencies that are close to one another but not equal, that create constructive and destructive interference at different places. And so I did not draw frequencies F1 and F2, but I did draw the beat frequency. And the beat frequency is equal to the magnitude of the difference between those two frequencies. And what the beat frequency looks like is it has places where there is quite a large amplitude and places where there's a quite small amplitude. And the difference between those places with the large amplitude and the places with the small amplitude is that at the large amplitudes, constructive interference occurred between the two separate waves, and they produced a larger amplitude. And at the small amplitudes, waves 1 and waves 2 interfered destructively and formed a smaller amplitude. And so what we're observing is the large and small amplitudes creating those loud and soft sounds. Now I'd like to talk a little bit about something called a standing wave. And in order to do that, I need to talk a little bit about reflection. So first, I just want to mention that if I send a wave pulse toward a boundary, it will reflect off of that boundary. And so two pictures that I have at the top, let's say that I just tie a rope very loosely around a pole. And I flick my wrist up and I send a wave pulse down that rope. The end of the rope is free to move up. And so what happens is the wave pulse arrives, the end of the rope moves up along the pole, and the wave pulse gets reflected back away from the pole. It comes back toward me. Now I'd like to do the same thing, but the boundary is going to be fixed in place. So maybe it's tied more tightly, or there's something holding it so that way it can't move up the pole. What will happen is that the wave will still reflect back, but it also inverts. And this is one of the things that's essential for forming a standing wave. In order to produce a standing wave, I need waves coming from the left and from the right, and I need those two waves to interfere, and I need there to be continuous wave pulses that are being produced, and I need places where there's constructive interference, and I need places where there's destructive interference. And so maybe you can imagine somebody on the left end of this string making the continuous wave pulses in this, all of those wave pulses hitting the fixed boundary, reflecting, inverting, and coming back, and then interfering with the subsequent wave pulses that the student is making. And this will form a standing wave. A standing wave that has visible nodes and antinodes. And they're forming, as I said, due to constructive and destructive interference that are traveling, of waves that are traveling in opposite directions. And maybe it looks something like what I've drawn below, where those green dots represents the nodes. A node is by definition a place in a standing wave where there is zero displacement. And if you look at the standing wave, it'll look like it's not moving. In fact, that's why we call them standing waves. They don't look like they're moving to the left or to the right. Now, standing waves are produced by waves traveling to the left and to the right, but it looks like it's not moving. The interference pattern forms these nodes, which I'm showing in green, and the antinodes, which I'm showing in yellow. And at any given moment, if I took a picture of this, say somebody was shaking a spring back and forth on the floor, it might look like the blue line, or it might look like the red line, but it won't look like both. As long as I've got a good camera, it would only look like one of those two. But over time, it kind of plays a trick on our eyes, and it looks like everything's just moving or everything, this pattern is being maintained all the time. All the particles are moving up and down instead of left and right, because this is a transverse wave. So relative to the direction of the waves, which might be to the left or to the right, the particles are moving up and down. And one thing that I'm about to talk a little bit more about with these standing waves is the way that I could use a standing wave to generate an equation for the wavelength. So let's suppose that the entire length of that spring that I've drawn down below has a length L. One of the things that I want you to notice is that there is a relationship between the length of the string and the wavelength that can be expressed in a certain way depending on how I look at the nodes and the antinodes. So what I want to point out is that if I start at this first dot, maybe I'll trace that again in white. If I start at this first dot and I go all the way up, back through the equilibrium position, back to my starting point here, I get one full wavelength. And what I notice is that in this wave in total, there are 1, 2, 3, 4, 5, 6, 7 antinodes. And one wavelength of the wave occupies 2 out of those 7 wavelengths. Therefore, relative to the length of L, the wavelength is 2/7 of L. And for that reason, what we could do is we could say that the wavelength is equal to 2L divided by N, where N is the number of antinodes. And this is the basis for understanding how standing waves form and how we can use equations for the wavelength of standing waves to further understand how the waves look and what's going on with them. So now let's talk a little bit about standing waves in pipes. We talked about two different types of pipes, open pipes and open closed pipes. One thing that you just have to know is if the end of the pipe is open, then there has to be an antinode there. And if the end of the pipe is closed, then there has to be a node there. So for example, on the open pipe, I've made sure to make either end of this pipe not have a node. It has to be an antinode. And the only way that I can connect two antinodes on either end of the pipe is by having one or more nodes in between. And so the biggest wavelength that I can draw is the case where there's only one node between the two antinodes on either end of the pipe. And what I want you to appreciate is we need to be able to look at this, physically understand that it's an open pipe, physically understand that the open ends of the pipes have antinodes, and then be able to imagine or picture what fraction of the wavelength I could be or am observing inside of that pipe. So let's look up at the blue wave that I have drawn above. If a wave starts at equilibrium and goes to its maximum displacement, that's 1/4 of the wave. If it then goes back to its equilibrium, the length between these 2 points here would again be 1/4 of the wavelength. So each one of these things is 1/4 of the overall wavelength. So every time something goes from maximum displacement to equilibrium, that's 1/4. And so what I notice for this first top left picture for the open pipe is that it goes all the way from equilibrium to the maximum amplitude, all the way from equilibrium to the maximum amplitude. Each one of those is 1/4 of the overall wavelength. Therefore, the wavelength is actually equal to 2 times the length. If I only see 2/4 of the wavelength, that's 1/2 of the wavelength. And 1/2 of the wavelength is the length of the pipe. Right down below I have that the length of the pipe is L. And if I only see 1/2 of the wavelength in the pipe, then the actual wavelength is twice as big as the pipe, or 2L. And the way that I reconcile this and the way that I represent this is I call this the first harmonic. I call this the first harmonic. And so we're going to define a variable n, which stands for the harmonic number. And this is n equals 1. Because down below, if I plug in n equals 1, I get 2L divided by 1, which is 2L, the exact length of the pipe that I determined up above. And so let's figure out what the next harmonic is, the next one that I've drawn down there. What I observe is that it goes from maximum displacement to equilibrium, so that's 1/4 wavelength, and then from equilibrium to maximum displacement, a second quarter wavelength, and then from there back to equilibrium, a third quarter wavelength, and then lastly a fourth quarter wavelength. So that is 4 quarter wavelengths of a wave. And what I notice is that it went from one place all the way through equilibrium to negative amplitude, back to the same position. So clearly it looks a little bit strange, but that is exactly one full wavelength. And so what number do I need to plug into my equation down below in order to get a wavelength that's equal to L? Well, if I changed n to 2, the 2's would cancel, and the wavelength would be equal to L. And so this is the second harmonic. And so what we learned about open pipes is that every single harmonic can fit inside the pipe. N equals 1, n equals 2, n equals 3, any integer value for n. The difference for an open closed pipe is that if one of the ends are closed, then that means there has to be a node there. And so here I've drawn the biggest possible wavelength that I can draw. The biggest possible wavelength that I can draw is one where the node is on the left-hand side, and then there's an antinode on the right-hand side with nothing in between. And what I notice is that it goes from equilibrium up to its maximum displacement, which is 1/4 wavelength. Therefore, if this is the biggest wave I can draw that corresponds to the first harmonic, then in order to make the equation work, I would need to have a 4 in the numerator. So that way for the first harmonic, the wavelength is 4 times bigger than the length. And if the pipe has a length L, then the actual wavelength of this wave is 4 times bigger than the pipe, or 4L. And so now let's see what the harmonic number is of the next wave. It goes from equilibrium to maximum displacement, back to equilibrium. That altogether is 1/2 of a wavelength. And then I see 1/4 of a wavelength here because it goes from equilibrium out to the maximum displacement. So 1/2 is 2/4, and then an additional quarter is 3/4. So actually, the wavelength is 4/3 of this pipe. Right? If I plug in 3 for n, I would get 4/3 of L as the size of the wavelength. And maybe this makes some sense if I extend the graph or extend the diagram of the wave out a little bit. So it starts at equilibrium, it goes all the way up, comes back through equilibrium all the way down, and then all it needs to do is go from this maximum displacement back to equilibrium once, just like that, in order to get one full wavelength. And that extra amount that had to be extended was 1/4. Therefore, the wavelength is 4/3 of L. And so if that's the case, then the harmonic number was 3. And one of the things that we learned about open-closed pipes is that we can only produce the odd harmonics, 1, 3, 5, 7, and so on. We also talked about closed pipes. And closed pipes can work just fine for producing standing waves. There just has to be a node on both ends. And we also produce standing waves in springs, and we're able to use the same equation as I had in the previous slide. So make sure you know how open-closed, and closed-closed systems work for how you generate those wavelength equations and how you understand what the pictures of what the standing waves look like. Make sure you're comfortable with nodes and antinodes and how they appear in these different kinds of objects. The last couple of topics here, we're going to talk about sound. And we know that the speed of sound is 343 meters per second. And one of the reasons, or one of the places where that number comes from, is that the speed of sound depends, just like the other mechanical waves that we study, on the physical properties of the medium. So for sound, that's things like temperature and density. So if the temperature goes up or down, or the density goes up or down, the speed of sound will change. But for a given medium, for example in air, the speed of sound is constant, and for air that number is 343. Now if I tap on a piece of metal, the speed of sound is communicated along the metal much faster because the density of the metal is much greater than the density of air. And if the density is much greater, then the atoms are more close together, and when I hit some of the atoms are able to vibrate back and forth more quickly and send the sound along it a lot faster. And so the closer the molecules are together, the atoms are together, the faster the speed of sound can be communicated. So in air, the speed of sound is relatively slow compared to things like a metal. However, what's good is if we have sound waves occurring in a given medium, for that medium the sound waves travel at a constant speed, and so we can use the pretty easy relationship of v equals distance divided by time, the speed is distance divided by time, to solve some interesting physics problems. For example, if we have a motion detector, the way that motion detector works is it sends out wave fronts, little sound waves. Typically, you hear a clicking noise next to the motion detector. It sends out a wave pulse, and because we know that the sound travels at 343 meters per second, then if those wave pulses bounce off of an object and return back the other direction, and then are received back by the motion detector a certain amount of time later, then if we know, or if the motion detector knows how much time it took for those wave pulses to return, and we know that the speed of sound is approximately 343 meters per second, then it should be able to work out how far away that object was. And so practically speaking, the speed of sound is a good technique for measuring the amount of time it takes for something to happen, or measuring how far away something is, because it is something that moves at a constant speed. The last thing I'd like to talk about is the Doppler effect. And we need to talk about this because it's a good application of the speed of sound and frequency and some of the things we were learning about waves. So let's see here. I have a speaker in the middle of the screen, that little red box, and around that speaker are wave fronts that are coming out. So the speaker is sending out sound waves in every direction. And there's a little car on the left-hand side, and it's traveling toward the speaker. And what's going to happen is, as it travels toward that speaker, the wave fronts relative to the car are going to bunch up, and they're going to get closer to each other. And so the relative motion between the car and the speaker is toward. It's moving toward the speaker. And if it's moving toward the speaker and those wave fronts are bunching up, then they are going to observe a higher frequency. However, if that same car is traveling away from the speaker and the relative motion is away, it's moving away as opposed to toward, it's moving away from the speaker, then the observed frequency will be lower because those wave fronts relative to the motion of this car are going to be more spread out. The wave fronts don't catch up to the car as easily if it's traveling away from it, and so it appears as though they've spread out, and that car would observe a lower frequency. Now, a couple of final points about the Doppler effect. First, this top point, which is written in yellow, somebody who's a stationary observer just standing there, they would observe the real frequency, or the true frequency, or the frequency that the speaker is actually emitting. There's no motion relative to the speaker, and so therefore they just observe the actual frequency. And lastly, here the picture that I drew had the observer of the sound, this little car, moving toward or away from the speaker, but it's just as simple to say, let's have the observer be stationary and use a source of sound that is in motion. Make sure you're familiar with the two words source and observer. The observer is the thing observing the frequency, and the source is the thing producing the frequency. And just remember that the Doppler effect is this change in frequency due to the relative motion between two objects. As I get closer to an object or further away from an object, it does get louder or quieter, but that is not the Doppler effect. The Doppler effect is the change in the observed frequency, higher or lower, due to the relative motion between two objects.